Hello, we continue studying operations on linear maps and matrices. So this time we'll look at composition of linear maps and the corresponding effects on matrices, which we call matrix multiplication. To have a composition possible, we have to have a pair of composable functions or maps. So let's imagine that we have the first transforming n vectors into m vectors, and then we have the second which can follow up transforming m vectors into n vectors. And both of them are linear. But even without them being linear, we can form what is called a composite. And the way of writing it is to change the order. F has to be applied first. And since we apply our maps from the left, we have to write it on the right first. So the recipe of computing this new transformation on a vector v of length n is this. First compute f, and the result you feed into g, and that is the composite. So first, again, I'm going to make sure that this new transformation is linear if f and g are. And again, linearity consists of two conditions. I have to see that my new transformation, this composite, is additive and it is preserving scalars, assuming that I have these properties for f and g. So let's first check additivity. Imagine two vectors of length n, u and v, and we compute their sum and we feed them into the composite. That means, sorry, it's g first, f second. That means that we have to compute our composite in this two-stage way. First do f and then follow with g. When we do f, we can rewrite this answer as a sum. And now we have a g evaluated on a sum of two vectors. Whatever they are, we can rewrite them as a sum of values of g on those vectors. But now we have f followed by g on some vector, f followed by g on some vector. That is what we call the composite. And the composite is now evaluated on two vectors, u and v separately, and then summed up. And that is additivity property for this map. The second property, preserving scalars, can be checked analogously. Just follow with the flow. We write first the answer according to the definition. Then we use the fact that f is linear, so it preserves multiplications by scalars. And we can rewrite this value as the product of f on v and the scalar c. And then we could put c through g and have this answer, which is just scaling of the value of the composite on the same v. So both properties are a linearity. We proved it. And since this is a linear map now, we can compute its matrix. Again, it's good first to introduce a reasonably good notation for this matrix, and it is sort of again imposed on us if we remember that, say, F on the vector V is a product of the matrix, whatever F matrix is. This time I'll call it B. And then G on the vector W is a different sort of vector, is M vector, will be the product of matrix A with this W. So the matrix B transforming n vectors into m vectors will have to be of size m by n. Matrix A transforming m vectors into L vectors will have to be of size L by m. And then when we iterate these transformations, when we compose them, so what is G composed with F on vector V? It will be G applied to F of V, and the first is F of V is matrix B multiplied with vector V, and G applied to any vector is matrix A multiplied by this vector. So that's what we have for just spelling out what the ingredients are. But then what we want to see is the matrix of this new linear transformation. This Fourier transformation will transform vectors of length n into vectors of length m. So the matrix will have to have the size L by n, L rows and n columns. And it's natural to call it the product of A and B. So if we just introduce this notation, so whatever C is, we just call it, it is computable out of A and B, and we just call it the product. And immediately we will have a nice rule. So when we have the product of A and B, two matrices, they can be multiplied if their dimensions match in the middle. The number of columns of the first is the number of rows of the second. It's just that the corresponding linear maps meet in the same place. So if we have such dimensions, we can multiply two matrices, and the result will be called the product. And then we'll have the rule that when we multiply a column with the product, it's the same as if we multiply this column in succession with the second matrix first and then with the first matrix afterwards. So that is the rule which just comes from the notation which we introduced here. So just calling it the product makes matrix multiplied with a vector associative. Finally, let's compute this matrix C. So what is this matrix? Matrix C will have these dimensions, so let me just call its entries C with indices. We'll have L rows and n columns. And the general recipe is to compute the matrix. I need to feed in this transformation basic vectors of length n one by one, and then use the results as columns. That is, the first column is just a transformation, is evaluated on the first of the basic vectors. And all the way to the last, when the last basic vector is fed into the transformation. The rest is just computing or rewriting what the ingredients are. So this is the result of applying F first and then G to what it is. Let's write the matrix of F, this B matrix, for what it is. So B is of dimensions m by n. And then we have to apply F first to this coordinate vector, to this basic vector, and that means that we are just looking at the first column of matrix B. So what we have here is G applied to B11 up to BM1. All the way to the last column of the matrix we compute, and that will be G evaluated on whatever F is on the last coordinate basic vector, and that is the last column. So will be we'll have B1n, BMN sitting inside. So these are the columns of the matrix we're computing. And that is not the end. We can now look at what G does to those columns. And G does what G does to any vector, multiplies it with A. So let's just write our answers as products of matrix A, the matrix of the transformation G, multiplied by the columns which are values of F. And let's now spell what A is. A has the size L by M. And then we just multiplying this A with our columns which are answers for F. And what we will have is, in the first column, it will be A11 times B11 plus all the way through A1M times BM1. So that sum is the answer for the first position in the column. And all other positions are computed similarly till the very last, where we will have AL1 B11 plus all the way through ALM BM1. And that is just the first column. But all other columns are computed similarly. So for the last column, what we'll have is A11 B1M all the way through to A1M B. Sorry, it's correct. 1M BM. I'm confused slightly. So the position is in this matrix C is this 1n. It's just the column which I wrote. No, I wrote it correctly. It's 1n. Yeah, that's what I wrote incorrectly. And then all the way till the last component of this column, where we'll have a L1 B 1M 1n all the way to a LM BMN. And that is the end of the matrix. So that is what we called the product of matrices A and B. I'll write them again. And the general recipe, if we want our matrix C to have coefficients little c's, so this little c with indices I and j, c sits at the intersection of ith row and j's column. So the general recipe is the following. We have to, according to this rule, we have to take elements from matrix A, which are all sitting in row I. That is the first element. And the last element in row I will be IM. And then we have to multiply them with a column of matrix B with number J. And then we have to take the sum of all these products, and this sum will be just the answer for the matrix entry in arbitrary position ij. And that is the same as to do what, say, is happening here. It is just taking columns of B and then multiplying them with matrix A, for example. So that is it. We'll continue studying properties of matrix operations in later videos. See you then.